Hello and welcome to Double Word Physics, Electricity. Let's continue from where we left off last time, which was IV graphs. So in this episode, I want us to talk about energy. That's energy being given to a wire or a bulb or any form of component, be it a motor or anything, in an electrical circuit. So looking at a wire, I left you with the idea that as the wire got hot, the resistance became greater. And I didn't really explain why that was the case. I don't like that because we're physicists, we're meant to explain everything. So if we think of this little coulomb of charge here as traveling through, the coulomb itself or the electron itself doesn't travel particularly quickly, but the energy does. So we'll call this this little guy charge. Okay. As he travels through, what happens is as we know from before, he can be involved in collisions with these other ions. And previously we were worried about how much energy he lost going through, and that was to discuss resistance and voltage and things like that. But law of conservation of energy says that you don't create or destroy energy, you simply transfer it from one place to another. So if this little coulomb of charge hits here and loses some energy and then continues on its merry way, then logically that energy must go somewhere. That energy, as with all collisions, goes into the object that it collided with. Okay, and this little object here, if I group them together, previously was maybe oscillating around a little bit, is now oscillating a little bit more. Okay, bouncing about. Okay, the more times this gets hit by coulombs of charge, if I have, remember, hundreds of these things passing through in a given time period, okay, gets hit once, starts oscillating a little bit, gets hit twice, going through, he's now oscillating quite a lot. Okay. If you're oscillating this much and all the others are doing the same, then the odds of the third guy getting through scot-free are pretty limited because he's covering a huge area here, comparative to his size, that this little guy here has no chance of getting through here without being involved in a collision as well. And that causes this to oscillate even more. And it's kind of a cascade system that the more it oscillates, the more the collisions are, so the more it oscillates. And that's what causes the heat, because heat is simply the kinetic energy. It's the movement of these particles. The faster they move, the hotter the thing is. And so the hotter it becomes, the more it vibrates, and therefore the more resistive it is because it hits more of these guys on the way through, because they're taking up a greater effective area. Okay, got that? So hot objects are highly resistive. I certainly found that when it came to dating girls. The hotter they were, the more resistive they were. Okay, so moving along swiftly. If we're talking about the energy lost by these coulombs of charge, then we need to have an equation for doing that. That's what physics is all about. It's all about predicting what goes on. So let's get ourselves an equation for the amount of energy that we are losing over a given time. So the energy that's being used by a particular kind of group or a particular wire or a particular piece of equipment is equal to the current traveling through it, I, multiplied by the voltage that it's using. Okay, so the current times the voltage, which makes sense, the number of coulombs in a second multiplied by how much energy each of those coulombs is getting, multiplied by how long, T for time, how long it's been running for. So I is current, and that's measured in amps. V is voltage, measured in volts. T is time, measured in seconds. And E is energy, measured in joules. Alright, now this will work for any component or work for any full circuit. Okay, same as Ohm's law, it operates between any 2 points you choose on any particular circuit. So for example, if I have, let's build ourselves a little circuit, nice little simple test circuit. So I've got a cell there. That's a cell, not a battery, because it's only got one big line and one small line. You become a battery when you've got a group of two of those. Get myself a, let's go for a resistor. Why change the habit of a lifetime? So I've got a resistor, got that, and let's be properly nerdy and put in the polarity of my battery. Okay, so that side's plus, not hash, that side's plus there, and that side is negative there. All good? Alright, now let's say that flowing around this circuit we have a current of 2 amps. So 2 amps going on there, and let's say that the voltage being used by this particular resistor is well, it's going to be whatever the battery is. So that's let's call it a 3 volt cell. It's a 3 volts. Okay, so we've got 2 amps, we've got 3 volts going around there. Now there are a few things I can do straight off. Straight off I can find the resistance of my resistor, that R is equal to V divided by I. Okay, so the resistance is equal to 3 over 2. So R is equal to 1.5 ohms. Okay, so back to symbol. And no need to do that, just to remind us from earlier videos that this is fine. Ohm's law still works here. So between for this whole circuit, that's a 1.5 ohm resistor. Okay, now what we really want to know is how much energy this thing's using up over a given time. So let's give ourselves a time period. Let's say for 30 seconds. We have that E is equal to IVT. Some people like saying is E equals ITV, then they can remember it by the TV station. Up to you. So E is equal to 2, which is the current, times the voltage, which is 3, times the time, which we said was 30. Okay, so 2 times 3 times 30, that's 6 times 30, which is 180 joules. Okay, so in a time of 30 seconds, this resistor will use 180 joules. And it's as simple as that. We'll do one more complicated, or slightly more complicated example, but beyond that, it just basically is, here's the equation, crack on. Okay, so this one we will have, let's do a parallel circuit. Okay, so we'll do a parallel circuit for the sake of it. Okay, so little parallel branch there, little parallel branch there. Out we come around this way. That goes around there, like that. Bet you're loving the drawing of the circuits, aren't you? Don't lie, I know you are. Okay, so copy that there, pop that there. Is the absolute weirdest thing talking to yourself. Oh well, at least you're not trolling me yet. Right, so let's call that a 2 ohm resistor. So 2 symbol, W for that, 2 ohms there, and another 2 ohms down at the bottom. Okay, so we've got 2 equal resistors wired in parallel with each other. I'll give you a starting voltage of 2 volts out of the little cell, and off we go with a current of, we should do conventional current, which goes from positive to negative. To force a habit of mine doing negative to positive. And let's give you a 1.5 amps, okay, just to make numbers awkward. Okay, so 2 volts, 1.5 amps, and I'm going to ask you to find the energy given out in each resistor in 20 seconds. Now if you think you've got a handle on this, pause the video now and have a crack at it. Try it in pen and paper and then come back and see how we get on. Okay, so energy given out in each resistor in 20 seconds. For each resistor we want to know E, so that's an unknown. We will know I, logically, we have to, but we don't know just yet. We also don't know V, but we do know that T is equal to 20. So far we know very little. So time to apply some logic. Okay, so the current is 1.5 amps here. So as it travels around, we get no choice, 1.5 amps, 1.5 amps here, and we get a choice here. Okay, so at this point, we get a choice. 2 ohms and 2 ohms, that's identical resistors. So I know that half of my current will go this way and half will go that way. So pick a resistor, they're exactly the same. We'll go with this one. So if half the resistance goes this way, I should now know that through this resistor we have 0.75 amps of current. Okay, so 0.75 coulombs every second. And the same is true down here as well, 0.75 amps down there. Now, consider a single coulomb of charge traveling out here. He's just left the battery, he's got 2 volts. Round he goes, still got 2 volts, still got 2 volts, haven't encountered anything to take my 2 volts from me. 2 volts, 2 volts, 2 volts. Here I get a choice. We've decided to go top route, so let's go that way. 2 volts, 2 volts, 2 volts. Okay, go through here, I'm going to lose some voltage, and then I have to arrive back at the battery with nothing. So I had 2 volts here, I have to have nothing here, so I must have given that 2 ohm resistor my full 2 volts, because there's nothing else to take it from me. Okay, and if I'd chosen to go the other way, that would have also been true, 2 volts down that way as well. And remember, this was our rule, that the voltage on any 2 parallel branches is exactly the same. So we've got 2 volts and we've got 0.75 amps. So we can update our information here. We know that that's 0.75 amps now. We know that the voltage is 2 volts. We're happy that they're all the correct unit. So we just pop it into E equals IVT. So E is equal to 0.75 multiplied by 2 multiplied by 20. Okay, so E is equal to 30 joules. So 30 joules used in this resistor, 30 joules used in this resistor. And that's all there is to it. All you have to do is figure out the voltage, current, and the amount of time. Watch out for minutes. Nasty that way. You get questions that say how long or how much energy is used in 5 minutes. Make sure you change your time into seconds, and we're all happy. See you next time for a chat about power.